My name is Bryce Bolin. I'm currently a postdoctoral scholar at Goddard Space Flight Center in Greenbelt, Maryland. I'm studying asteroids and comets with ground and space-based facilities, including those that are located in Hawaii. Just last couple weeks ago, I was actually at the IRTF, the NASA Infrared Telescope facility, where I was observing asteroids located in the inner main belt, just exterior to the orbit of Mars. Where I am now, I'm in Nice right now, where I did my PhD. I did my PhD on the dynamics of asteroids, which have a common collisional origin. Kind of touching base on my old supervisor here. So yeah, sorry if y'all can see. Yeah, I'm on the beach right now. It's actually quite a beautiful view. I don't know if I can turn this around if y'all can see.
Yes, please.
But yeah, this is the plage. Yeah, so the beach here in Nice it's not sand, it's like these rocks. I don't know if y'all could see that. They call them pebbles. So it's kind of funny because there's this theory for planet formation called pebble accretion, and it was code which describes how the icy cores of giant planets were formed from tiny pebbles, and it was partially developed here in Nice. So it's kind of funny. Nice is very famous for its pebble-covered beaches, where it's planetary formation theory of pebble accretion was partially invented.
Bryce, I'm from a part of the world where there's another famous pebble beach.
Oh, where is that?
You know, I'm in California, but Pebble Beach is in Monterey, famous for its golf tournament and all that.
Yes, I've heard of that. I've heard that that golf tournament is pretty famous. Isn't that's a? I didn't realize Pebble Beach was in California though. Wow.
It's a little bit south of Santa Cruz. It's about an hour south of Santa Cruz, in sort of the Monterey Carmel area, right?
Yeah.
Oh, sorry. I was just going to say one of our we had a Python tutorial earlier, our first for June, and one of the mentors, Geronimo, is actually also in Nice right now.
Oh, really?
Oh,
wow.
Yeah, he's in Nice right now working on PhD there. Yeah, so two people in Nice today that we get to chat with.
Is he at the observatory?
I think so. He's a PhD student in astro over there.
Yeah, he's at the university. I forgot the name.
And Lam is in Marseille, of course, Laboratory Astrophysics in Marseille, which is not far from Nice, but he's in Nice, exactly, Jamaica. He mentioned that.
Well, I'm going to go there tomorrow, so I'll have to reach out to him.
I'm going to put his name in the chat.
I'll send you an email and connect you guys. Maybe we could jump into something that the students may actually recognize as part of your work. This is the awesome, really exciting. Last year, there's this green comet. People may have heard about that. Was visible for a while. And Bryce was actually one of the co-discoverers of this comet. This is 2022 E3. I'll drop that in the chat. And Bryce usually has this awesome background with that comet in the back, which is just absolutely amazing. So I'll drop the name of that comet in the chat, and maybe Bryce, you could talk a little bit about the ZTF found the comet, and some background on that as it relates to the rest of your research.
Yeah, sure. Yeah, so that was pretty interesting discovery. So I made that discovery while I was working on a telescope project called the Swiftly Transient Facility, which is located in Mars. But I was working there for a few years from 2019 to 2022-ish. But almost 10 years prior to that, I was in Hawaii where I was working on the Pan-STARRS telescope, similarly doing discovery of asteroids and comets. And so I've made with Pan-STARRS as well as CTF. I've discovered maybe 40-ish comets. So when I discovered CTF, the E3 comet, it was like, okay, you know, like another comet, right? It didn't really, at the time, it didn't really stick out to me as being particularly, you know, noteworthy. We found the comet using this this kind of this special comet detection pipeline that I worked on at Caltech that uses deep learning to identify comets and wide field CCD images. But our pipeline found it, and to me at the time, was like, okay, this is just another, let's say, validation that this is a working. I have a little presentation here. I can show you all. Is that okay? Is it it's all right if I share my screen?
Yeah, I'll let it.
Yes, please, of
Absolutely.
course.
Okay, so here we go. So let me see if I can do this in a way where I can, yeah, picture says 1,000 words, right? So yeah, so this is for example Comet 2I Borisov. This is the second interstellar comet that was found with by knowledge in the world, mankind's knowledge, the second interstellar object known to humankind, as seen with CTF. And so it's circled here in this green circle right here. And so you can see in this image, there's also lots of other, let's say, features. These are actually these little splotches in the background surrounding where this comet is located. At the center of this image are subtracted stars. So the idea is that you can take two images of the night sky and you subtract one image from the other. You'll remove all static sources. So anything that remains post subtraction was where one source was not located. And the other is what you would call an astrophysical transient. So when I arrived at Caltech in 2019, the CTF pipeline had this peculiarity where it could not find comets. It was fine-tuned to find supernova and like stellar objects, but it was not good at finding extended objects. Comets, by their definition, are extended and actually be spatially resolved, actually have a spatial extent that is larger than the intrinsic spatial scale of the imager, as determined mostly by astrophysical, by the actual atmospheric scene. So the typical atmospheric scene is on the order Palomar around 1 to 2 arc seconds. So an extended object, by definition, or a comet, would be something that would be significantly more extended than 2 arc seconds. Something would be in the extent of, say, several arc seconds across. But by definition, this for an extended object, the CTF pipeline rejects all detections that it finds that comes through its program that are extended. It only retains those that are point source like, because they're only interested in supernova. Supernova are distant, exploding stars that, even though they're exploding, they're not resolved. They're detected at the scale of the image. So I noticed this when I arrived at Caltech, that we weren't going to be able to find interesting comets, make interesting comet discoveries. And so this was a 2I, the second interstellar comet was discovered by Gennady Borisov in the Crimean Peninsula in the September of 2019. But I noticed that CTF actually imaged 2I Borisov several months earlier in May 2019. But because of the way the pipeline is configured, where it's optimized looking for supernova, it rejected all extended objects, and by definition, it rejected 2I Borisov. So the discovery of 2I Borisov could have occurred and been done by CTF if it had the capability of discovering extended objects. So this is why on this slide here I say the CTF pipeline all extended sources, including comets. Possible solution: use deep learning as a workaround to identify comets on a per image basis. So I worked with Dmitry Duev, who is expert on deep learning. He was a scientist at Caltech, expertise in machine learning. Sorry, Raji, you have a question?
Yes, please. If you could go back one slide. If I had 10 hands, I would put them up. I have many questions. Sorry, if I could. So does the ecliptic plane run sort of at around 2 o'clock through the comet, or what is the direction of the ecliptic?
I'm not sure exactly the direction of the ecliptic where this where it is in this image.
But I'm actually looking for the negative version of this image, right? It's a difference image between.
Yes. So this is an image between the science frame. It's a difference image made between the science frame that a single image that is taken by the CTF survey and a reference sky frame that is made accumulated over many observations of that same part of the sky.
I see.
So
I see. So you wouldn't see the negative version of this image. I see. So you have a static image that you've subtracted off from the time variable image.
That's correct.
Okay. And the elongation is more or less in the vertical direction for this thing is that real, that elongation?
Yes. So this image is oriented north up and east to the left. Sorry, the cardinal directions aren't indicated on there, but Borisov, let's see if I can pull up sorry, doing this kind of impromptu here, but I'll show you what Borisov looks like as imaged by Hubble Space Telescope. This is a combination of data that I took and public data of Borisov in the data of Borisov in the public Hubble archive. But Borisov is more or less extended in kind of the north and south direction. It has a tail that is leading out towards the northwest, but the brightest portions that you can see in the ground are in the north and south direction. So when we're looking at this right here, the extended portion I was seeing, I mean, it's very faint. So this comet was detected at the time. The limiting magnitude of CTF in a single 30-second exposure is a single 30-second exposure.
Wow.
The limiting magnitude of CTF in a single 30-second exposure in our band during dark time is about 20 and a half. And Borisov was it had a total integrated brightness of around 18 and a half, but when you take into account the diffuse nature of it, was actually quite a marginal detection.
Close to the detection limit then.
Yes.
Yeah. This is beautiful.
But,
sorry to have interrupted, but this is beautiful.
No, not at all. Not at all. This is a great question. Great discussion. Yeah, so I mean, this was kind of, the motivation factor was, okay, we lost the opportunity to discover this interesting object, and it's due to the limitations of the CTF pipeline. So I worked with someone who was an expert in machine learning and training a deep learning neural network to identify said comets on a per image basis. So these are kind of the process here. So you have the raw science image. So each of these is a triplet of image or 4 different comets. So for each of these triplets, the leftmost one is the raw science image. The middle one is the static sky. and then the rightmost image is the difference between the two. So you can see here on the sky, on the science image, you see there's the comet. As long as the background stars and science, and on the reference image, the comet is not present, but the stars are all located right there. And the difference between the two, only the comet remains. But there are some, let's say, residuals from this subtracted background stars, but the only real effect here is the comet. So this is for 114P Wiseman Skiff, and 29P Swashburn Fox 1, which is a very famous comet, and C2019 D1 Flewelling. This Heller Flewelling, if you know her, she is currently at CFHT working on the pipeline for MegaCam. She was a comet discoverer before that at the Institute for Astronomy, working on the Atlas telescope, but she's now in Waimea working on the Canada Prince White telescope. And she's great. It's very thankful to her discovery there, helped train our neural network model. And then 26BP, not. But we trained our neural network on thousands of observations, known comets taken by CTF over a couple of years. So this is kind of machine learning, let's say, enthusiasts here. You can, this is a little bit of an overkill that we use a variety of different neural network structures and combining them together into a single output that gives us the probability of an object being a comet or not. But more or less what we are doing here is that we have this what a convolutional neural network means is that basically you have this kind of kernel that sweeps over an image. It doesn't look at the entire image all at once. It looks at pieces of an image, little bits at a time, and it comes up with a way of saying, okay, I think I found something that looks comet-like in each of those little pieces. So what this neural network is doing, what this network is doing, is coming up with ways to organize that information. But the input is basically a triplet of images. You have the science image, the reference image, and the difference image. And the output that you get, this P, this probability in X and Y, it's a probability that a source is a comet and X and Y is the location within the image. But yeah, this is if you're interested in learning about neural networks, feel free to check out this reference or screenshot this to kind of look at how our network might work. I won't go into too much because that could be a discussion in itself how neural networks work. They're very interesting, but we're actually working on a new version of this now, where we actually use fully integrated networks, fully connected networks, in combination networks. But that's going to be Tails 2, say the second version of Tails. So this is kind of the performance of Tails as a function of the probability. So this is the false positive rate, the false negative rate as a function of probability. So for let's say more than 80%, the portion that are in either the false negative or false positive category is less than a few percent. So it's a pretty accurate, say, network. Does not result in hardly any false positives or false negatives. So this is some tests that we did. So we were able to successfully identify 2I Borisov in our data, the second interstellar comet, as well as some other known comets. But most importantly, we started to make discoveries, unknown comets that were unknown to prior human knowledge. So we made the very first discovery using very first AI assisted or AI powered, however you want to buzzword you want to give it, was made, a discovery was made in August of 2020 with the discovery of C2020 T2 Palomar. And using just a very small percentage of data, we found 10 other comets. So this is a list of discoveries, comet discoveries that was made between 2020 and 2022 using this Tails network. T2 is the very first AI-assisted comet discovery, but there's a number of other of these. This is kind of a spaghetti noodle diagram showing the different comet orbits. They're mostly long period comets, that they're on orbits that are almost parabolic. They don't really form a closed loop. So they come from very distant solar system, and they're very borderline, marginally bound, gravitationally bound to the sun. So it's just kind of interesting. The majority of the comets we discover are short period comets. So I highlighted here C2022 E3 had a perihelion of 1.11. That's the closest distance it comes to the sun. An eccentricity of nearly 1, so it's has a parabolic orbit and an inclination of 110 degrees, which makes it a retrograde. So it's almost going perpendicular to the plane of the ecliptic. So I don't know if y'all noticed, but in January and February of 2023, it was starting to become fairly bright, where you could see it from the ground with the unaided eye. So it's on the cover of Newsweek, Time Magazine, Sky and Telescope, astronomy picture of the day. So it kind of got a little bit out of hand. But I woke up, I forgot I discovered this comet in a year prior, in February and March of 2022. And I completely forgot about it. And I woke up one day and checked my email and was getting dozens of emails from people asking me to talk to me about the discovery of this comet. So I was like, okay, all right. But here are the discovery images that were from March of 2022 made with the CTF. So this left panel right here shows a single 30-second R band exposure. It was located at R8 of 20 and a declination of 1 degrees. And it doesn't look very extended in the single image. It looks marginally extended. So that's the thing. Tails, even though it's trained to recognize things like tails and coma, it actually also works on objects that are marginally extended relative to background stars. So in these images, the E3 comet had a spatial extent of 3.5 arc seconds, while the background stars had a spatial extent of around 1.5 seconds. So that was enough to elevate its probability that it's a comet, which prompted me to submit its detection to the Discovery Asteroid and Comet Discovery Clearinghouse, known as the Minor Planet Center. So here is the orbit of C2022 E3. It's at the time, this is showing it's in X, Y, and Z coordinates at the time of its discovery, March 2nd of 2022. So it's actually seen coming north above the ecliptic. And you can see how it kind of has this kind of downward trajectory through the ecliptic. So it has a very high inclination of 110 degrees. It has a perihelion of 1.1 AU and came within 0.28 AU from the Earth in early February 2022. That's when everyone was taking those pretty pictures, and reached a magnitude of 5. And I actually drove out to the desert. I was in LA at the time. I drove out to Joshua Tree, and I was actually able to see it with just first by eye. It's very faint, but then with a little amateur telescope, I was able to see it really nicely with binoculars. So we also took a spectrum of the comet.
Oh, we have some more questions here. Sorry about that.
About
So
6300 line?
Yes, so we have a spectrum. This was taken by the SADM machine. This is the spectral energy distribution machine at Palomar on the Palomar 60-inch. This is a spectrum between 400-ish nanometers and 900 nanometers. At a spectral resolution of about 200. And it's a very low resolution spectrum, but we can still see there's some features here of cometary emission features. Like there's this big spike over here. This is cyanogen gas that is at 380 nanometers, and triatomic carbon and diatomic carbon at 400 and 510 nanometers respectively. And then we have forbidden oxygen line, actually caloric oxygen, but the combination of the two has this big spike here at 620 nanometers.
And Bryce, that glitch at 7600 must be telluric absorption that's not corrected properly.
That's right. That's right. Because it's pretty. This is with an IFU.
Oh, I see. It's with an IFU. So this is the A band, the atmospheric A band then.
Yes. So IFU is nice because it gets you the comets, coma, extended objects. Very nice. Supernova people, they like IFUs because it allows them to get the contribution.
Bryce's connection cut out.
Oh,
he would-
no.
What he was going to say is supernova people like to use the IFU to get a spectrum because then they can distinguish between the. Bryce, you cut out for about the last minute. So you were going to say that the IFU is preferred by supernova people because they can distinguish between the spectrum of the host galaxy and the supernova?
That's right. That's right. I don't know I don't know anything about about supernova observations with IFUs, but that's what I understand, that the idea behind the SCDM, the spectral energy distribution machine, is to follow up supernova, and we just were able to use it for a comet. But it's very nice for comets too, because comets are extended objects, and an IFU allows you to map the spectrum of the comet. Now, someone has a question here.
Oh, no, yeah, that's just me.
Oh, hi.
Quick question. Okay, so we have about 6 minutes left. Thank you again for joining us from the beach there, Bryce.
So sorry.
You're amazing. Thank you. Raja had asked, I'm going to lower my hand. Raja asked earlier if you could maybe in this last few minutes talk to us about the intravenous asteroid that you were a part of detecting, which is
Sure.
is a very new kind of asteroid, right?
Sure, I can show that. So let's see. I can show very quickly because there's a whole story to it, but but I wanna, since we have very little time, I'll show it very quickly. So these are the discovery images of the very first inside the orbit of Venus asteroid. It's made on January 4th, 2020. There's a Sky and Telescope. Yeah, this is it's a very good, very nice article here. Yes, on Sky and Telescope, written by David Dickinson. He was a really great science communicator to work with, but he wrote this great article about the discovery. So these are the discovery images right here that were taken on January 4th of 2020. So you can see the asteroid was seen in all four images. It's moving kind of in the northeast direction. And the orbit looks kind of like this. I don't really like this image right here. In my opinion, I have a better version of the orbit, a better picture of the orbit. Let's see, I'll switch back to my keynote. Let's see, sorry, so this is the orbital diagram of very first inner Venus asteroid. So it's given a name Alo-Shaxnam by the Palma Band and near Palomar. They speak San Luiseno. They speak the San Luiseno language, and in that language, Alo-Shaxnam means daughter of Venus, or Venus girl. So I thought it was very appropriate. I'm really happy they came up with that name. It's because it's the very first asteroid located inside the orbit of Venus. So this is an orbital diagram within our solar system with the orbit of Alo-Shaxnam in it. So the orbit of Mercury is in red. The orbit of Venus is in this kind of light blue color, and Earth is in purple. And Alo-Shaxnam is in this kind of green color right here, this olive green color. And it has an aphelion that is the maximum distance that it will have in its orbit from the sun of 0.65 astronomical units. Venus is around 0.72 astronomical units. So it's about 0.07 astronomical units inside the orbit of Venus. So it never crosses the orbit of Venus. So this was the very first asteroid of this type that was discovered, and it was made at Palomar Observatory in January of 2022.
It's practically
So
Mercury
just to have
crossing, right, Bryce?
Yeah, it just skirts outside the orbit of Mercury. So it's actually in a pretty interesting orbital configuration with Mercury. It's
Is it in some kind of resonance? Is it in a 3-to-1 resonance with Mercury, or 3-to-2 resonance? Sorry.
Yes, it's in a 3-to-2 mean motion resonance with Mercury, kind of like how Pluto is in a 3-to-2 mean resonance with mean motion resonance with Neptune. So being in this 3-to-2 mean motion resonance actually protects it from close encounters with Mercury. So that's probably why its orbit has lasted as long as it has, because it hasn't had any Mercurian encounters. Yes, this was made using the twilight survey at the Palomar Observatory. That was also used to find the E3 comet. Yeah, we also found a bunch of other asteroids that are kind of like it. So there's another category of asteroid called the Tiras, which are located inside the orbit of the Earth. They don't cross they cross the orbit of Venus, but they don't cross the orbit of the Earth. They're actually located well inside the orbit of the Earth. So we found 4 of those in addition to Alo-Shaxnam, which was a significant portion at the time of the known Tira objects. Someone here has a hand raised.
Oh, it's me again, Bryce.
Oh.
Yeah, no, it's me. I just I wanted to respect your time. I knew you were already doing something else.
No worries.
Now that we're at the top of the hour, I wanted to ask you, this is amazing. I had not seen these yet, so I'm really thrilled that you could that you had the time to share them with us. Could we take questions? Do you have a few minutes to take questions from any of the students?
Sure.
Feel free, you all, to raise your virtual hand or post questions in the chat. And while we're waiting for that, Bryce, could you maybe tell us if you participated in any programs in high school, like, something similar to the Science Internship Program, where you were able to first kind of learn some much needed skills that you used later on in your career? And maybe you could also talk about some extra experiences you had while you were in undergrad and grad school that led you to what you're doing today.
Sure. So when I was in high school, there weren't really, at my high school, there weren't really a lot of classes that
I basically ran out of the science curriculum pretty quickly at my high school. It was available at my high school, but I was very lucky in the sense that originally from Orlando, Central Florida area. And that despite being in, what you might have heard about Florida and its educational system, what was nice about it was they had a pretty generous program called dual enrollment, which allowed high school students to enroll in courses at college and community college for free. And they would actually even purchase textbooks for you to go. So as a high school student, I was able to take classes in computer programming and mathematics and chemistry that were at the kind of sophomore to freshman level of college. While I was in high school, it was immensely helpful, especially for the computer programming. I was lucky to have a great teacher who unfortunately passed away a few years ago, but he's French Canadian. But he lived in Orlando and was an expert in software. That was learned C plus and Java. Without that program, there would have been no way. They would not offer this classes at my high school. So this was a very nice program, and yeah, it was a huge help. And surprisingly, I don't want to diss my fellow classmates in high school, that despite the generosity and availability of this program to everyone, I couldn't really get anyone else in my high school interested in enrolling with me. I was the only person in my high school class taking advantage of this amazing program, and everyone else seemed to want to do other things after high school, because it was night classes. You had to take these classes in the evenings, so it was like school after school. So it was like extra school on top of school. So I guess they didn't want to do that. But yeah, that was pretty amazing. And then when I was in undergrad, graduates, they didn't really have REUs, or they did, but they were like kind of a new thing. So REU is research experience for undergrads. And I didn't really understand what research was or what science was when I was interested in physics. I was a physics student. I was really interested in physics problems and doing, like Griffith's, textbook type physics problems, or like the famous one for electromagnetism that has the all the different 20 different R scripts for various variables. And then there's Griffith's quantum physics that has that Schrodinger's cat on it. And, so that's what I thought physics was. I thought physics was like, oh, you're just working on, more and more advanced physics problems that you're sitting at a desk, and I didn't have any idea that, okay, wow, this is a scientific enterprise that goes on behind it. So RUs were kind of just starting out, and I think it was my junior or senior year, I think I saw some advertisement for RUs, but I didn't really, I thought research was like, I didn't really, like you go to the library and you sit in the library all day and you read a bunch of books or something, and you write a book report or something at the end of the summer kind of thing. I didn't realize that you're actually, doing science, exploring previously ventures. But I was able to eventually talk to the right people who put me in contact with a new professor who was looking for undergraduate students that could be involved in a project that was at this particle physics laboratory in near Chicago at this lab called Fermilab. And this was a project related to studying the properties of neutrinos, various subatomic reactions that produce neutrinos. The experiment that used, it was basically a giant tank of mineral oil, and it would study neutrino interactions, what's called Cherenkov radiation. As these particles are going through this tank of mineral oil, it would detect various light signatures using multiplier tubes.
to try to piece together what was going on, what kind of reactions were taking place in this tank as the neutrino and other subatomic particles were passing through it. So this supervisor was I was not a very good undergraduate researcher, but it taught me at least opened my eyes to what that science is something that is actually occurring today. We actually are expanding our knowledge past what we are reading in these old these textbooks that are covering basically knowledge that was established sometime in the early 20th century. When it comes to things like quantum mechanics, undergraduate quantum mechanics, classical mechanics, and electromagnetism, that there is actually science going on the cutting edge, and it's a huge enterprise, multi-billion-dollar enterprise through various funding agencies, things like projects like the Large Hadron Collider, product that's most recently with the construction and launching of the James Webb Space Telescope, which was a multi-billion-dollar endeavor taken by worldwide collaboration. So it's kind of very, very roundabout kind of thing, but I was able to kind of luck into someone who was willing to hire me as a undergraduate researcher and kind of getting my feet wet in the world of research. I wasn't a very productive undergraduate, but I definitely learned a lot relative to what I did prior to. Nowadays, it's pretty nice to have these REUs, research experience, for undergrads, which are programs that go out of their way to try and recruit undergrads and get them involved in research. If you have an opportunity to do one of those, I highly recommend it. Trying to applying and getting involved in those, finding ways to get involved in those. Yeah, I wasn't really involved in research until my graduate school. Towards the end of my master's, I started working with a professor who was using data from the Cassini spacecraft to study the optical properties of Saturn's rings via stellar occultations observed by the spacecraft, by the Cassini spacecraft, using an instrument that could take very rapid, very high cadence series of images of the rings close up as the spacecraft was flying over the rings, and could observe a star that was behind, occulted by the rings, and measure their optical depth and particle size properties. And I made enough progress in that project that I was able to go present my results at a conference in France that so happened to be where someone was looking to hire people. And so I ran into someone named Robert Jedicke, who's at the Institute for Astronomy in Hawaii, working on a project called Pan-STARRS. I mentioned that a little bit before. He was looking to hire someone to help him with the project. And I spoke with him, and I said I was interested, and he offered to hire me. So it was kind of, not the typical path of people. I didn't come from a very scientific background. My parents aren't scientists. We're probably from the furthest type of people you would expect to be scientists. But no one in my extended family is a scientist, so I had no one in my immediate social vicinity to tell me what science was or what people actually do for science as a career kind of thing. But I eventually found my way into it.
Bryce, that's amazing. It really is. It's really nice to hear about a non-traditional path to being such a successful astronomer.
Well, thank you. You flatter me, but thanks.
It's true.
I appreciate it.
Absolutely. And I've talked to you before about how I think you should certainly I support you in sharing your experiences whenever you can, because it is rare to hear and nice to hear these non-traditional paths, so that many people know that there are many different routes to get where they are trying to go, no matter what field that they're in, but especially in planetary sciences and in astronomy in general. A few people have messaged me asking if they could follow up with you. Is it okay if I share your email with them if they have further questions?
Sure, sure. So let me put my website in the chat. It needs to be updated. This doesn't have. I have updated every few months, so I try to keep it updated. I'll try to keep it updated more frequently than that in the future. But if you want to, it has all my contact information on there. If you want to reach out to me, I have Twitter, Instagram. Email is the best way. My email's in the top right corner. It's let me see if I can put it here. Yeah, here's it's bolin.astro@gmail. Please don't email my NASA email, because NASA email is very difficult to access when you're off the NASA campus. So if you email my NASA email, I won't see it. But if you email my Gmail, I can reply to you pretty quickly.
Excellent. Bryce, thank you so much for this in-depth look behind the scenes of a comet hunter and discoverer. We're so grateful for your time, and certainly look forward to Shadow the Scientist sessions with you later in the year, Bryce. Enjoy Nice, and hope you have a good rest of your evening there on the lovely beach.